Hello dear students, welcome to the Numericals. Last class I have solved 5 numericals. Now sixth one, a beam of light consisting of 2 wavelengths 650 nanometer and 520 nanometer is used to obtain interference fringes in Young's double slit experiment. They are asking find the distance of the third bright fringe on the screen from the central maximum for wavelength 650 nanometer. And in second case, what is the least distance from the central maximum where the bright fringes due to both the wavelengths coincide? So here, first note on the given data. Sixth one, lambda 1 is equal to, let us take lambda 1 is equal to 650 nanometer. Or this is equal to 650 into 10 to the power minus 9 meter. Lambda 2 is equal to, lambda 2 is equal to 520 nanometer. 520 nanometer. This is equal to 520 into 10 to the power minus 9 meter. In first case, find the distance of the third bright fringe on the screen from the central maximum for wavelength 650 nanometer. That means you just imagine yourself in this double slit experiment when you are going to use a light of wavelength 650 nanometer. During this case, find the position of the third bright fringe. Position of the third bright fringe with respect to lambda 1 650 nanometer. First one, position of the third bright fringe for wavelength lambda 1 is equal to 650 into 10 to the power minus 9 meter. So we know that expression for position of the nth bright fringe. We know that xn is equal to n into lambda. Here lambda is nothing but lambda 1 into capital D divided by small d. Third bright fringe x is equal to 3 is equal to 3 into lambda 1 650 into 10 to the power minus 9 into capital D divided by small d. Here they have not mentioned capital D and small d, that is the distance between two slits and distance between double slit screen and observation screen. So we can consider these two one as it is, that is capital D and small d. Then position of the third bright fringe from central bright fringe x3 is equal to 650 into 3. We just multiply this one. Into 10 to the power minus 9 capital D divided by small d meter. This is the answer. Because here we don't know capital D and small d. Next case, or you can write 1950 capital D by small d nanometer. That is also correct answer. Then second one, what is the least distance from the central maximum where the bright fringes due to both the wavelengths coincide? When we are going to use lambda 1, we will get interference pattern, arrangement of bright dark, bright dark, bright dark, bright dark, bright dark, like that. Again, when we are going to use lambda 2, we will get interference pattern on the screen, bright dark, bright dark, bright dark, bright dark. Among these two patterns, one fringe is going to coincide with each other. That means with respect to lambda 1, fringe with respect to lambda 1 and fringe with respect to lambda 2. And here we have to find out position of that fringe at which the fringes of two interference pattern coincide with each other. So we don't know here, it may be a fourth, it may be a fifth, it may be a sixth. You just observe lambda 1 is greater than lambda 2. Fringe width for this lambda 1 is greater than fringe width for lambda 2, that is beta is equal to lambda into capital D divided by small d. Therefore, I am going to say nth fringe of this 520 nanometer coincides with n minus 1th bright fringe of 650 nanometer. We can consider like that. Therefore, in second case, let nth bright fringe, let nth bright fringe of wavelength lambda 2 520 nanometer coincides with n minus 1th bright fringe of wavelength lambda 1 that is equal to 650 into 10 to the power minus 9 meter or 650 nanometer. Nth bright fringe of lambda 2, n into lambda 2 coincide is equal n minus 1th bright fringe, n minus 1 of lambda 1. Now we can get the name of that fringe. So which fringe with respect to lambda 1 and with respect to lambda 2 coincide with each other. Solve this equation. N lambda 2 is equal to n lambda 1 minus lambda 1. Lambda 1 is equal to n lambda 1 minus n lambda 2. Lambda 1 is equal to n into lambda 1 minus lambda 2. Then n is equal to lambda 1 divided by lambda 1 minus lambda 2. N is equal to lambda 1 650 nanometer into 10 to the power minus 9. Lambda 1 650 into 10 to the power minus 9 minus 520 into 10 to the power minus 9. Common factor is 10 to the power minus 9. 10 to the power minus 9, 10 to the power minus 9 get cancelled. Then n is equal to 650 divided by 130. Solve this one. So here you will get n is equal to 5. That means fifth bright fringe with respect to lambda 1 and lambda 2, they are coincide with each other. Then what is the position? That means the distance of this fifth bright fringe from central bright fringe. Position of the fifth bright fringe from central bright fringe xn is equal to n into lambda into, so here I am going to take lambda 2 into capital D divided by small d. If you are going to take lambda 1, you should take n minus 1 here. Again you will get the same answer. Then xn is equal to n is equal to 5. So here 5 into lambda 2. Lambda 2 is equal to 520 nanometer into 10 to the power minus 9 into capital D. We don't know capital D. Take that capital D as it is, divided by small d as it is. Then x5 is equal to this is equal to 2600 into 10 to the power minus 9 capital D divided by small d meter. So that is the position of the fringe with respect to 520 nanometer. If you are going to take 650 nanometer, then you should take n minus 1. Next one, in a double slit experiment, the angular width of a fringe is found to be 0.2 degree on a screen placed 1 meter away. The wavelength of light used is 600 nanometer. What will be the angular width of the fringe if the entire experimental apparatus is immersed in water? Take a refractive index of water to be 4/3. Seventh one, angular width in double slit experiment. Let us take a theta 1 is equal to 0.2 degree. On a screen placed 1 meter away, that means capital D. The wavelength of light used, lambda, is equal to 600 nanometer. What will be the angular width of the fringe? Take theta 2. If the entire experimental apparatus is immersed in water, take N2 is equal to 4/3. So here N1 is equal to 1. In first case, when angular width is equal to theta 1, that whole apparatus is in air medium. When that whole apparatus immersed in water, what is the angular width in that double slit experiment? So this type of questions usually going to ask in competitive examinations. There is no need of much more calculation to solve this one. So here we know that from Snell's law, the ratio of sine of angle of incidence to the sine of angle of refraction is equal to constant. That constant is known as the refractive index of the medium at which we can view change in path of light. Now I am going to use the same concept here. from Snell's law, sin I divided by sin R. So instead of I am going to consider sin theta 1 divided by sin theta 2. This is equal to constant n21, or this is equal to n2 divided by n1. Relative refractive index, absolute refractive index. So clearly here theta is very small. For small angles we can consider sin theta 1 is nearly equal to theta 1, sin theta 2 is nearly equal to theta 2. For small angles theta 1 and theta 2, sin theta 1 is equal to theta 1 and sin theta 2 is equal to theta 2. Therefore, we can write theta 1 divided by theta 2 is equal to, given data is in terms of absolute refractive index, n2 divided by n1. So here they are asking angular width when that whole apparatus immersed in water, that means theta 2. Angular width when the apparatus immersed in water of Ri, n2 is equal to 4 by 3, that is theta 2. Theta 2 is equal to cross multiplication theta 1 into n1 divided by n2. Substitute the values. Theta 2 is equal to theta 1 0.2 n1 1 n2 4 by 3. So 3 in numerator. Then theta 2 is equal to six by 40 or 3 by 20. Theta 2 is equal. Solve this one. So this is equal to 0.15 degree. So this is the angular width. So angular width decreases. So clearly 0.15 is less than 0.2 when that whole apparatus immersed in water. Next, eighth one. What is Brewster's angle for air to glass transition? Take refractive index of glass to be 1.5. So usually this question is going to ask for 2 mark. Eighth one. Refractive index n is equal to 1.5. So they are asking to calculate a Brewster's angle. Brewster's angle or polarizing angle, both are same. We know that expression for a Brewster's law, that is a refractive index of the medium is equal to tangent of the Brewster's angle or polarizing angle. From Brewster's law, we can write n is equal to tan IB. So here IB is nothing but polarizing angle. Then IB is equal to polarizing angle is equal to tan inverse of refractive index. Then polarizing angle is equal to refractive index 1.5. Tan inverse of 1.5. Then IB is equal to, search this value in natural tangents, you will get the answer. So approximately here you will get a 56.3 degree. 56.3 degree. That is Brewster's angle. Next, ninth one. Estimate the distance for which ray optics is good approximation for an aperture of 4 millimeter and wavelength 400 nanometer. So to solve this one, for a good approximation of ray optics, that is a Fresnel distance is equal to small a square divided by lambda. So in this case, diffraction effect can be neglected. That means ray optics is valid. Or when d is very less than Fresnel distance, in that case also ray optics is valid. So here, for the good approximation of ray optics, ninth one, for an aperture, that is A is equal to width of the slit, A is equal to 4 millimeter, 4 millimeter, that is 4 into 10 to the power minus 3 meter width of the slit, and wavelength of light lambda is equal to 400 nanometer, 400 nanometer, that is equal to 400 into 10 to the power minus 9 meter. So we know that we have Fresnel distance, we have Fresnel's distance, that is ZF for a good approximation of ray optics is equal to A square divided by lambda. Then Fresnel distance is equal to A square that is 4 into 4, 16 into 10 to the power minus 6 divided by 400 into 10 to the power minus 9. 4 into 10 to the power plus 2 into 10 to the power minus 9 is equal to 10 to the power minus 7. So in numerator it becomes 10 to the power plus 7. Therefore, Fresnel distance is equal to 4 into 10, 40 meter. So, Fresnel distance for a good approximation of ray optics. Tenth one. The 6563 angstrom H2 line emitted by hydrogen in a star is found to be redshifted by 15 angstrom. Estimate the speed with which the star is receding from the earth. Receding means it is moving away from the earth. In case of redshift, frequency decreases and hence wavelength increases. So here they have mentioned wavelength of H2 line. Lambda is equal to 6563 angstrom, or this is equal to 6563 into 10 to the power minus 10 meter. In a star is found to be redshifted by 15 angstrom. They have mentioned change in wavelength delta lambda. You have to take that 15 angstrom as a change in wavelength. The delta lambda is equal to 15 angstrom. 15 into 10 to the power minus 10 meter. Estimate the speed. They are asking speed, that is V, relative velocity between source and observer. So in a redshift, or expanding path. Redshift is nothing but expanding path. Frequency decreases, wavelength increases. So therefore, I am going to consider apparent wavelength in case of redshift when source is moving away from the observer. Apparent wavelength lambda is equal to lambda naught into 1 plus V by C. Wavelength increases 1 plus change in wavelength. that is delta lambda is equal to apparent wavelength minus original wavelength. Lambda naught is nothing but original wavelength. This is nothing but apparent wavelength. Then change in wavelength, because given data is in terms of change in wavelength, for that reason I have considered change in wavelength. This change in wavelength is equal to apparent wavelength. We know that expression for apparent wavelength, lambda naught into 1 plus V by C minus lambda naught. Then this change in wavelength is equal to lambda naught into 1 lambda naught plus lambda naught into V divided by C minus lambda naught. Lambda naught minus lambda naught plus lambda naught get cancelled. Then delta lambda is equal to original wavelength, relative velocity between source and observer divided by speed of light. Then relative velocity between source and observer, this is equal to change in wavelength into speed of light divided by original wavelength. Then relative velocity is equal to, substitute the values, delta lambda 15 into 10 to the power minus 10, speed of light 3 into 10 to the power plus 8 meter per second, original wavelength, so this is nothing but original wavelength, lambda naught. Lambda naught is equal to 6563 into 10 to the power minus 10 angstrom. 10 to the power minus 10, 10 to the power minus 10 get cancelled. Then relative velocity is equal to 45 into 10 to the power 8 divided by 6563. Then V is equal to, solve this one. So approximately here you will get 6.86 into 10 to the power plus 5 meter per second. So this is the relative velocity between source and observer. So like this they may ask apparent frequency, apparent wavelength, original wavelength, like that. If given data is in terms of frequency, then you should take nu is equal to nu naught 1 minus V by C, that is in case of red shift, frequency decreases. In case of blue shift, frequency increases, that means nu is equal to nu naught 1 plus V by C, and hence wavelength decreases. In case of blue shift, lambda is equal to lambda naught 1 minus V by C. So like this, if you know the way how to use the formula, then you can solve any type of numericals. The first thing, you should separate all the formulae in this chapter. Then recall the formula again and again. So then you will get the perfectness in that chapter, and you can solve this type of numericals. So these things are not required. Only for your understanding purpose I am going to write here. You just write in a redshift, apparent wavelength, and start from this step. So this is usually asked for 3 marks. Okay. So in the next class we shall see few more numericals.